pi turns out to be 4. Now, if we define pi as the ratio of the circumference of the circle over the diameter, which is twice of the radius. Here's why. So here we're going to inscribe the circle inside a rectangle. No, square. So if I change this into that, do the same thing. Change this into that. Change this into that. And do the same thing here. Change this into that. So this time the circumference of the outside whatever shape is still the same as the original square. So if I repeat this process, change this into that, change this into that, change this into that, 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 this into that. So the area of the circumference of this shape is still the same as the original square, right? So here we're going to make sure the horizontal line segments are equal to each other. Right? Horizontal line segments are equal to each other. But the vertical line segments are not necessarily equal to each other. Right? But still, if we repeat this process over and over again infinitely, then in the end, the outside shape, circumference, will be always equal to that of a square. Right, but this square radius is r. Right? So here is 2r. Circumference is 4 times 2r, 8r. So according to the definition of pi, circumference of the circle over 2r. Right? So here the circumference of this shape is going to closer and closer to the circumference of the circle. Right? So eventually the circle circumference is going to equal to 8r, right, as the square, the same as this shape. So eventually we have 8r, 2r, 4. So what exactly went wrong? Now if we use this 1/4 of the circle and observe that, so if we equal partition, right? So here, like I said, I'm going to make sure that horizontal line segments are equal to each other. But the vertical line segments are not necessarily equal to each other. Right? So here I'm going to calculate the area of this rectangle. Now, looks like as long as I repeat dense enough, more and more this process, in the end, the curly triangle area, they sum up approaching 0. So in other words, the rectangle area sum up to approaching 1/4 of a circle. Looks like that. But just because of that doesn't necessarily mean the path length is equal to this path length. No. So here's why. 0, x, y. So to calculate this rectangle, so the height of the first rectangle is just r. Height of the second rectangle is h2. height of the third rectangle is h3. The height of the last h4, hn. So the area, like I said, when n approaches infinity, looks like a definite integral. A Riemann sum divided into n equal parts. Then, of course, this Riemann sum, right, each rectangle is evaluated at the left edge of this small subinterval. Left edge, left edge, left edge, left edge. So indeed, the Riemann sum. So the limit would be the definite integral. The definite integral would be the area under the curve, which will be the 1/4 of the circle. Pi r squared over 4. That's its limit. Right? The limit of the sum of areas of these rectangles. Right? Really approaching the 1/4 of the circle area. So in other words, the sum of the area of this curly little triangle is really approaching 0. Right? So no problem. Just to clarify. So here, even though we have this shape, right? It's not approaching. The area is not approaching this triangle. Is because, like I said, we even partition the horizontal line segments equal to each other. But that doesn't mean the vertical line segments are equal. In fact, they are not equal. Right? So we cannot say that the area is approaching this rectangle. Right? It's approaching the 1/4 of the circle area. Right? But like I said, even though the path length of this path is not equal to the path length of this path.